Okay, so in the last video I said I would make an improved version of it because I wasn't too happy with the time it took to run, so this is going to be that improved version. So there's going to be a bit of math talk at the beginning of this, and if you already understand what the lowest common multiple and the highest common factor, how to find those using prime numbers, then you can skip this bit. But basically what I'm going to do is I'm going to quickly Google how to find them, and I'll possibly leave a link in the description. If not, just Google HCM and LCF, so highest common multiple and lowest common factor. You'll find loads of different stuff on it. I'm looking right now at the BBC Bite Size website. So yeah, it tells you how to do it. It says to find the highest common factor, so you're looking for the highest, not the highest common factor, the lowest common multiple is what we're looking for, the smallest multiple, the same as the lowest common multiple. So to do that, it says what we need to do is we need to split each number into its prime factors. So for this example, it uses 24 and 36. I'm going to actually drag this over. You get to read this on the screen at the same time as me. Okay, hopefully this works. Yeah, there we go. So you can see here the lowest common multiple is what we need. So to find the lowest common multiple, we need to think about which list is most of each factor. So it uses 24 and 36. So 24 separates into 2, 2, 2, and 3, and 36 it separates into 2, 2, 3, and 3. 24 is the most 2's, 36 is the most 3's. So the lowest common multiple, you take the most 2's and the most 3's. Multiply them together, you get 72, and as you can see, 72 is actually a multiple of both of these. It's actually 3 times 24 and it's 2 times 36. So yeah, hopefully that makes sense. I'm not going to go into detail on that. If you need to learn more about that, then go Google it. It's not too difficult. Something you learn at GCSE, so like 15-year-olds, something like that. So yeah, we're going to use that. So same problem. We're going to use that method though to solve it. So what we're going to do is, if I open up, which problem was it where we have to prime numbers, prime factor? It'll be in this one. So problem 3. Okay, so if we look at problem 3 here, you can see my solution for it. We took the target, we took the potential factor, list of the prime factors, we appended that list. So this list ended up with every prime factor in it. So I'm going to run this. I'm going to see what it did exactly. I don't think it actually took that long to run, so it should be fine. Okay, maybe it did take a while to run. There we go. So it did actually give us a full list of the factors, so that's really handy. So we're going to use this code. What I'm going to do is I'm going to copy over what I need. I'll probably just copy it all and delete the bits I don't need. So if I copy this into here, so we don't need this, we've already got this. So we don't need to time it yet, we'll do that later. Now, target, we're going to keep that. Potential factor, we're going to keep that. The list, we're going to keep that. So we don't need this. Now, what we want it to do, we want to take all our numbers up to our target, like up to our 20, and we want to say for all these numbers, take them down to their prime factors. So how do we do this? So first of all, we're going to have I'm going to call it LCM up to. So this is going to be 20. This is going to be what our target was from our previous example. It's basically just going to be the number we're going to go up to. So now for I in range 1 to LCM up to +1, we actually want to run this code down here that I've just put in. So to pull that all along. Now target is going to be I instead. Potential factor is going to be 2. So what I'm going to do, I'm going to get rid of 1 here. I'm going to start at 2 because we know 1's not prime. It's pointless me having that in. So I'm just going to run this. I think this will give us 20 lists or 19 lists, whatever, of all the factors. Doesn't seem like it is though. I know why, because I haven't actually changed. So this target here, all these targets need to be switched to... No, that's not right. Okay, so why is that not breaking? Oh, because I'm running the wrong thing. Okay, that would make sense. God, that's painful when you make mistakes that bad. So there we go. So we see for 2, its prime factors 2. We see for 3, its prime factors 3. For 4, its prime factors are 2 and 2. For 5, it's 5. 6, it's 2 and 3. 7, it's 7. So you can see here the prime numbers all just have 1 factor. So this is actually finding as prime numbers as well as finding as prime factors. So this is what we're going to use to basically use this lowest common multiple theorem on. So to find the lowest common multiple, what we have to do is find the most of each number sort of thing. So what we'd do is we'd say which one has the most 2's in. So you can see the most 2's is here, there's 4 of them. So we'd do 2 times 2. So if I do this on a calculator, if I do this manually, we're going to actually see the answer. So can I capture this calculator somewhere? Nope. Okay, what I'm going to do, I'm going to type it into Python and then we'll run the code afterwards. So answer equals, so we're going to do all these 2's, so 2 times 2 times 2 times 2. I'm going to put this in brackets just to make it obvious where these numbers. Actually no, we don't need brackets because they're all going to be different numbers. Okay, so the 2's, now we're going to need to find the most 3's. So which one has the most 3's in? We've got 2 here, we've got 2 here, so 2 3's is the most we've got. So if I times by 3, then times by 3 again. Now there's the most 3's, and now the rest, there's actually not multiple of any other number because the next prime number after 3 is 5. And obviously 5 times 5 is 25, which is off our list. So now all we need to do, after timesing by all the 2's and 3's, is times by, so times 5, then times by 7, then times by 11, times by 13, times by 17, and times by 19. Now, if I print answer, that number right there should be the answer, and you can see 232792. If I go back to the answer, so you see 232792, 560, and then my answer was 232,792, 560. So it is actually the right answer. So now we've got the answer, but what we need now is a method of getting the computer to realise how to do this calculation right here, because obviously I've just done this manually and I'm not going to be doing that for everything we want to find the lowest common multiple of. So how do we do that? Now what I'm going to do is I'm going to say list of prime factors is equal to an empty list. Now each time I get a list of prime factors, I'm gonna list of this dot append list of prime factors. So what this is going to do when I print it list of prime factors. This is just going to put all of these prime factors, put all these lists into a list so that I can use that later on. So you can see here we've got 2 as our first entry in the list, 3, 2, 2, 5. So it's basically just one long thing of all of this, just so I've got one piece of data to work with basically. So if I just comment out this print statement up here because I don't need that, let's see when I run it again. There we are. So what I need to do now is I need to go through this list and I need to say which one has the most of each number in. So for each number in each element, so what I would do is I'd check the first one and say, right, there's a 2. So I need to find out which element has the most 2's, and then however many 2's it has, our answer needs to be multiplied by that. So we're going to have an initial answer. Answer is going to be 1 to start with. Now what we're going to do is I'm going to comment in what we're going to do here. So this is probably not beginner level anymore because this is going to be really messy and I'm probably not going to explain myself very well, but hopefully it's interesting if someone's following along. So we want to iterate over our list of list. So list of list is just this thing here, is just what I'm calling this. So we're going to iterate over that. Find each number and how many times it appears. Find the place it appears most. Multiply our answer by this number this many times. So we're going to take 2, so we're going to iterate over the list. So this is just, you know, like for I in length list, whatever. Find each number, so we're going to find 2 is our first number we're going to come to, and we're going to say, right, find out how many times it appears in each element. So it appears once here, 0 here, 2 here, 0 here, 1 here, and we're going to say what's the most amount of times it appears. Now we're going to multiply our answer by this number this many times. So if it appears 4 times, we're going to multiply our answer by 2 to the power 4 because we're going to multiply by 2 4 times. Hopefully that makes sense. So for I in range, no, what we're going to do is we're going to say for, so we're going to say for primes in list of list, print primes. So you see what this does, it just takes the elements and prints them back out, so it just does the reverse of what we did here where we added them all. It just takes each one, prints them out. So now we know that that's going to do that. We're going to say for prime in primes, print prime. Now what this is going to do is it's going to take each element of these elements, so it'll print out 2, then 3, then 2, then 2, then 5, then 2, then 3 is the hope. So you see that it does 2, then 3, then 2, then 2, then 5. So hopefully that makes sense. We're taking a list of lists and we're going to take out, so it's just now a list. Then we're going to take that list and we're just going to print out the individual elements. So what we want to do now is we want to say for prime in primes, so for each number in there, we want to search for that number. Is that how we want to do this? Let me just print out these primes again. That's probably not how we want to do this actually. What we probably want to do is we want to say okay, what I'm going to do, I'm going to create a new list. So list of numbers to check is equal to blank. Now for prime in primes, we're gonna list of numbers to check dot append if prime not in list of numbers to check, then we're gonna list of numbers to check dot append prime, and at the end we're gonna print list of numbers to check, and we can get rid of that now. Right, so this list of numbers to check right here, 2, 3, 5, 7, 11, 13, 17, 19, you can see this is all the prime numbers that are involved, all the prime numbers up to the number, so up to 20. These are all the numbers that we need to check through and say, right, how many times do you appear in each one? So now what we're going to do is we're going to say for I, sorry, not there, we're going to go down to, we'll start here, we'll start anew. So we've just had one for loop that creates that list. We're now going to say for primes in list of prime numbers to check. This section will be prime because it's going to be one number, sorry. So for the prime in the list, we're going to say how many times do you appear in each element of list of prime factors. So for prime, so first element's going to be 2. We're going to say how many times does 2 appear. So we're going to have a count variable. So count equals 0, because it could be 0 times it's appearing. Probably don't want that there though. God, this is getting confusing. I think I'm doing this a terrible way, but we'll see. We'll get there. So for primes in list of primes, if for I in primes, if prime is equal to I, count plus equals 1. Now where am I wanting this count to reset? So I want this count to reset after each primes, so right here count 0. Now we want to find out the most, so we need a max count variable. It's going to be right here. Max count is equal to 0. Now if count is greater than max count is equal to count. Now once all that's done, we're going to say print prime max count. Right, I'm going to run this, see if it works, and then I'll explain it afterwards. And it worked! I can't believe that worked first time. Okay, so what this does, in a really complicated way that there's probably a way better way of doing, is exactly what I wanted it to. It checks how many times each number appears. So you can see here, when it's printing the prime and the max count, so it's printed the prime's 2, and it says what's the maximum amount of times that 2 appears. Well, it's 4. So we know we want to times our answer by 2 to the power 4. Now the next one, 3 appears twice, so 3 to the power 2 we want to multiply by. Now we want to multiply by 5 to the 1, 7 to the 1, 11 to the 1, so on, so on. So if I add this line in, answer times equals, so that'll just mean the answer equals the answer times by some number. It's just shorthand in Python. It's like doing plus equals, just like that. It's just exactly the same, but times equals. Prime to the power of max count. So to the power of is just 2 multiplications. I'm not sure if I've already used that in another video, but if I haven't, there you go. That's how you do the exponential, or that's how you add an exponent in. You don't need to do these chevrons that I see a lot of people doing in like other stuff. And then we want to print answer. So we see right before that, if we come out of that and run again, there's our answer right there. So it does work. I'm very happy with that. And now with this method, what you can do is you can actually go say up to 100, and this should still work really quick. Like you can see there, that a huge number that it's just found incredibly quick. You saw in the previous code, like the first time I did this, when I was iterating through and doing like a brute force method, just doing this number up here, like 232 million, just doing that took like a minute, maybe longer. Whereas doing this number that is like, I don't know, let's do print line answer. So, whoops, string. So 41 digit number. So this number up here that I did, where's it gone? So this number is obviously 9 digits. Now, a 41 digit number can be done in just a fraction of the time. So if I actually time this, so import time. Now, so what I'll do, I'll time it down here. So start time is equal to time.time. No, I can't time it down there because if I do that, never mind, I'll do it up here. Start time equals time.time. Then print, and we'll use the string formatting that we learned in the last one. So print this. What we'll do, we'll say the answer is this took. This is digits long. This took seconds to find. Dot format, and then we're going to pass in, so the answer, the len string answer, and the time.time minus start time and go. Does that work? So the answer is this. This is 41 digits long. This took 0.002 seconds to find, so incredibly quick. If I open up the original one to this, so this one right here. Now we're just going to do 10 because this took ages. Import time start time time.time. Print answer is this took seconds to find. Dot format. Answer is x and time taken is time.time minus start time. Now, if we run this one, you can see it takes a similar amount of time, almost exactly the same amount of time, to do it on a 10 digit, up to 10, as it did to take up to 100 here. So if I change this number to 15 now, you can see that takes 0.29 seconds. Now if I do this on 15, that takes 0.001 second. So incredibly quick by comparison. If I change this to 1,000, I will eventually break this because these numbers are just insanely long, but you can see it's just found this number that is 433 digits long, and it only took 0.07 seconds. So in terms of efficiency, even though I've wrote way more code for this, as you can see this was just 20 lines, this one is 52. In terms of efficiency in code, obviously this one's better, but in terms of efficiency in processing, so if you're going to do this on a big number, you saw for yourself when I ran this on 20, it took absolutely ages. So yeah, I think this was well worth doing. Hopefully you understood at least some of this, but you can see there's many different ways to solve each problem. You shouldn't just always be looking at brute force stuff. Like this here, I think was the most obvious solution, to just check each number, and if it's not right, check the next one. But quite often there's improvements you can make to your code using like a mathematical trick or some like a little bit of clever knowledge. So yeah, this thing right here is a perfect example of that. So it adds a lot more code, and it was actually, I don't know how I got this to work first time. I was incredibly confused coding this. If you followed this, I'm pretty impressed. But hopefully you understand what it does. Just how it does it was, yeah, didn't make too much sense to me, to be honest. But hopefully you understand the benefits of doing stuff like this, like adding in the clever bits of code that can make your code work for extremely big numbers. So yeah, that's going to be it for this video. You can see this is still running, so this will be a while. I'm not going to wait while this finishes. Yeah, hopefully you enjoyed it. Subscribe if you did, like the video if you liked it, and I will see you in the next video. Thanks for watching.